Okay, so today's lesson, like I said, we've gone over before. We have talked about the difference between mass and weight, but we're going to go over it again. And I'm going to specifically look up more about what gravity is. So you can think of gravity as like a force field, but not the kind that's on science fiction shows like Star Trek where you go and touch it, it like stops anything from passing. It's not that kind of force field. But if this were the Earth here, right, there's an invisible field that's pointing towards the Earth. And any object, in the case of gravity, any object with mass will interact with that field and experience a force. Right? You're probably used to maybe magnetic fields. If any of you have played with magnets and little iron filings, and you get those shapes, those circular shapes around the magnet, okay, that's showing the field, the magnetic field. Okay, this is an example of the gravitational field. Now, it's important to note that gravitational field does have a vector property. Notice that the arrows are all pointing downwards, which, I mean, makes sense. If you drop something, it goes downwards, right? Anything with mass in the field will feel a force downwards. Now, in our previous unit, we talked about acceleration due to gravity, and we compared that all objects, no matter the mass, will accelerate downwards at 9.8 meters per second squared. And we gave it the symbol G. Well, that G we can call something else. We can call it the gravitational field strength. And we give it units newtons per kilogram. Now, a newton per kilogram is an equivalent unit to meters per second squared. You can actually see that if you look at Newton's second law. So if you write F equals ma, okay, if you rearrange that and divide both sides by m, you get F over m equals a. These units are newtons per kilogram, and that's equivalent to meters per second squared. So really, whether or not we say G is 9.8 newtons per kilogram or 9.8 meters per second squared doesn't really matter. The units are equivalent. But we usually say newtons per kilogram when we're talking about G as a field strength and we want to know the force, the amount of force that acts on a certain amount of mass. We talk about the field strength. If we're looking at an object's motion in a gravitational field, we like to talk about its acceleration. And so we say acceleration due to gravity, and we label it as meters per second squared. That's really the only difference. It's just context. Just pause. So let's try a practice question. So just to recall, we can calculate the force of gravity by setting it equal to the object's mass times the gravitational field strength, which on Earth is 9.8 newtons per kilogram down. Okay, so our first problem says the force of gravity on a 250 kilogram spacecraft on the moon's surface is 408 newtons down. So because we're on the moon, the value for the field strength, G, is not 9.8. That's only for the surface of the Earth. So this says, what is the gravitational field strength on the moon? Well, what do they give us? They give us mass, which is 250 kilograms. And they give us the force of gravity, which is 408 newtons down. And we want to figure out what that gravitational field strength is on the moon. Right? So looking at our equation, if it helps, you can draw a triangle. You can put Fg at the top, and then mass and gravity here, field strength. So if we're solving for the gravitational field strength, it's going to be the force divided by the mass. So G will equal our force divided by our mass, which is 408 newtons down over our mass, 250 kilograms. Put that on our calculator and we get 1.6 newtons per kilogram down. So that's our gravitational field strength on the moon. Alright, so comparing mass and weight. In English, we usually use those terms as if they're the same thing. Right? You might be cooking something, okay, I need 30 grams of flour, right? And that's how much mass I need. Right? But you go to your doctors and they say, well, how much do you weigh? Right? And I weigh, I don't know, 80 kilograms, for example. Okay, although I realize some people may use pounds. I don't use pounds. Okay, but it's still incorrect to use kilograms for weight in physics, because weight is the force of gravity that acts on something. It is whether or not something is heavy or something is light. And something is heavy and light because of the force of gravity pulling it down. It's not heavy or light because how much stuff there is. Okay? So mass, in SI units, we'll use kilograms. Okay, which, funny story is, you probably noticed, it's the only SI unit that actually has a prefix, right? Kilo. When we do distance, we do meters, right? Forces, we do newtons. Time, seconds. Okay? Energy, joules, right? No other unit actually has a prefix before it, like milli or kilo or centi or mega. Only mass does. And that's an interesting story. I'll post a good video for that we can watch later. But mass will be measured in kilograms in SI units, and weight will be measured in newtons, because it is a force. It's the force of gravity that acts on you. So if you were to go to the moon, right, which I would jump at the opportunity to do. I don't know how many other people would, but if you were to go to the moon, your mass would stay the same, but your weight would decrease, because the force of gravity acting on you is different. It's about 1/6 on the moon. Okay, I'll just pause. Question 2 says, an astronaut on the surface of Mars finds a rock, accelerates at a magnitude of 3.6 meters per second squared when it's dropped. Right, so on Earth, you drop something, you can do an experiment to see, oh, it accelerates at 9.8. This astronaut did this experiment on Mars and found it accelerates down at 3.6. The astronaut also finds that a force scale reads 180 newtons when the astronaut steps on it. What is the astronaut's mass as determined on the surface of Mars? So they're telling you the acceleration due to gravity on Mars, which is in meters per second squared, but the units are identical to newtons per kilogram. So I'm going to write 3.6 newtons per kilogram down. Right? And that's for Mars. Now when the astronaut steps on a scale, the scale is only reading 180 newtons. But remember, that's telling you your weight, not your mass. And your weight is the same thing as the force of gravity. So that's 180 newtons down. Now part A says to find the astronaut's mass. So to do that, you can look at your triangle and you'll see that mass equals the force of gravity divided by your gravitational field strength. Looking at those magnitudes, we have 180 newtons divided by 3.6 newtons per kilogram. You'll see newtons cancel and you'll get an answer in kilograms, which is 50 kilograms. Now, you guys are probably still used to thinking about your mass in pounds. So when you see that, you might not know if that's a lot or not. It's actually not a lot. That's a really tiny astronaut. Part B says, what should the force scale read if the astronaut stepped on the Earth? So if the astronaut comes back to Earth, the astronaut's mass does not change, right? Unless they ate a lot, but let's just say it doesn't change. Okay, so for part B, this is A. If we're back on Earth, we can calculate their weight, or the force of gravity acting on them, by taking their mass and multiplying it by the gravitational field strength for the Earth, which we know is 9.8 newtons per kilogram. So that equals 50 kilograms times 9.8 newtons per kilogram, which gives us an answer of 490 newtons down. And so if you wanted to figure out what your own weight actually is, so when your doctor says, what's your weight? Instead of saying whatever pounds or whatever kilograms, because both would be wrong, right? Take your mass in kilograms, if you know it. If you only know pounds, convert it to kilograms, multiply by 9.8, and then you can correctly say what your mass is in newtons. All right, last thing I want to talk about is a couple terms. We have free fall, weightlessness, and microgravity. Now, usually if you see astronauts on the International Space Station, a lot of people say, oh, they're weightless on there because they're floating around. But that's really a misleading term. Because remember what weight actually means. Weight means the force of gravity that acts on you. And the astronauts on the International Space Station, the value for the gravitational field strength, although it's not 9.8, it's 8.7. There's a lot of gravity there. Right? And so they experience weight. Well, they don't experience weight. They have a weight. It's just they have trouble measuring what that weight is because you can't stand on a scale because they're floating around. So if they have weight, and therefore because the force of gravity is acting on them, the big question is, why are they floating? And the answer is they're falling. Picture this. Here you have the Earth. Okay, this is actually Newton's idea. It's called Newton's cannon. So he imagined a large cannon. I think I actually have a picture of this here. There we go. So he had a large cannon on top of the Earth. This is a huge cannon if you take it to size. Okay? And if you launched a bullet or cannon, right, slowly it would go here. If you launched it faster, it would go further. And if you launched it faster, it would go further. But notice what's happening, right? As it travels, it's always falling towards the Earth, but it's able to go farther and farther because the Earth is curving away from it. If you can get it to go fast enough, it'll always be falling, but it will never fall down because the Earth continues to curve away from it that quickly. So the astronauts aren't actually in a weightless environment. It's the force of gravity that actually keeps them in orbit around the Earth. Without gravity, their space station would just fly outwards, never to come back. Gravity keeps them in orbit. So there's definitely gravity there. But they're floating because them and the space station that they're in is falling. Right? And so they're in free fall. And free fall, the term free fall means the only force acting on you is the force of gravity. I understand that's a hard concept to wrap your heads around, so I'm going to post a couple of videos. Let's watch some videos with some good animation. Alright, so let's look at the last example for this lesson. Here we have a 74 kilogram astronaut. That seems a little bit more reasonable. Goes up to the ISS on a mission. During his stay, the gravitational field strength on the station is 8.6 newtons per kilogram. So what's the mass of the astronaut? This is almost a trick question. Right? It makes you think like you want to calculate the force of gravity, but they give you the mass right there. 74 kilograms. Okay, so it's my way of testing to see if you really know the difference. So mass is 74 kilograms. Next it says, what is the difference between the astronaut's weight on Earth's surface and his weight on the station? So in this case, we're going to calculate both. We can calculate Fg for the Earth, which is mg for the Earth, and we can compare that with Fg, which is weight again, for the ISS, which is m times g for the ISS. Right, so on Earth, it's 74 kilograms times g we know is 9.8 newtons per kilogram down. Right, but for the ISS, again, mass doesn't change. That's still 74 kilograms. But the g we have is 8.6 newtons per kilogram. Alright, so if we just throw those onto our calculators, we'll get 725 newtons for the Earth. Down, of course. And on the International Space Station, 636 newtons. Down. But again, you couldn't actually stand on a scale on the ISS to test that because you're falling, the scale's falling, and the space station is falling. So it's kind of hard to stand on the scale. And it says, why does the weight of the astronaut change, but not his mass, when moving from the Earth to the station? Okay, well, weight changes because the gravitational field strength changes. You're further away from the Earth. The further you go from the Earth, the less it becomes. Although remember, you're not that far away. You're only about 400 kilometers up. Right? It just seems far away because it's so hard to get to. I mean, I can drive 400 kilometers, but I can't drive up 400 kilometers. That seems like a really, really difficult task. And it is. It's extremely difficult. Okay? So that's why your weight changes. But your mass, remember, is the amount of stuff you have. And that's not going to change. And then, again, we've talked about this, but why does the astronaut appear weightless on the station? It's because they're falling. They're falling, the space station is falling, and their scale is falling. Okay? But they never crash into the Earth because their high horizontal velocity, right, has them go around the Earth. So the Earth actually curves away from them.